much. I really appreciate the invitation to speak. Uh, and I really did enjoy the conference we just had a week or so ago down in Washington at George Washington University. That was a really pleasant gathering. What I'd like to talk about today is some work that I did uh, a year or so back with Margaret Nichols, who is now over at this Lucy Institute, Family Institute, over that's attached to Notre Dame. Um, this is about surface embeddings in R3, but I want to give R3 some structure. So it's actually R2 cross R. And I've got a question here. How do we do this? The question is, here's a knot, and for people who are familiar with it, you can see that this is actually out of Dale Rolfson's book on knots and links. And the question I have, this is a 661 knot presented here, is you see that it's positioned in a way that you can readily observe that it is the boundary of a surface. It turns out to be an oriented surface. How would any one of you go about calculating the Euler characteristic of the surface that it's the boundary of? Any ideas?
Are we supposed to see a shared screen? Oh, I
Are,
see.
are you, do you see a shared screen or not?
Oh, I need to fix myself. Okay, sorry. It's my problem, I think.
Uh, does
You
it,
can continue. It's my
or,
problem. Yeah.
or can other people see what I've got here on this Beamer presentation?
Yes.
All right. Okay. So any ideas on how you would just go about computing the Euler characteristic of this surface? So uh, uh, it's a nice surface and it's um, I'll actually shade it in here. Let's shade it in green here. Um, so it's this surface right here, and it goes around right here, goes over right here, it's up over here. So how would you compute the Euler characteristic of this? Anybody? Nobody?
Um,
No,
the surface deformation retracts onto a wedge of two circles.
right? You could do
Um,
that. You could do that. Yeah. So the wedge of two circles, you could go in that direction. So one circle goes around and follows the thing here, and the other circle goes around like this. And so you get the wedge of two circles, and the deformation retracts onto it. And then from there, you want to complete your thought,
the wedge of two circles is then like a has a cellular decomposition with one, I guess, zero cell and two one cells.
right? One zero cell and two one cells, and then you could do, um, uh, you know, what is it? Oh,
Evens minus odds, I think.
even it's minus it's alternating sum. One zero cell minus two one cells is it's a minus one. So that would be the Euler characteristic. And it's so you can see it as a disk with two one handles. So it's another way of thinking of two minus one. All right, I'm going to give you a different way of doing it. Let me get and the different way of doing it. So let me just stop annotating it. How do I go forward? Um, uh, is I'm going to do it by looking at its boundary And remember the Euler characteristic is -1. So here's another way of getting -1. What I do is I take the boundary and I orient it. And I'm going to compute what's known as the turning number. Here it's t, little t of the knot k, so that it's turning number. So the way you do this is, or one method of doing this is just pick a point where the tangent line to it is horizontal, and then you uh, move, sweep out along the boundary, and every time you come to another point where the tangent line is horizontal, you just check whether you reverse the orientation. It's either going to from left to right or right to left. So it starts off here at this point right here, and then it's up here, and as you trace it out, and that's pi. All right, it's gone pi around or half a turn around. And so I'm going to record that instance of a half a turn, and and so at half a turn counterclockwise. So counterclockwise is positive, clockwise negative. From here to here, it went and came down, and now it's still pointing the same direction. So even though it's still it's down here, it's horizontal, it's still pointing the same direction. So it started to turn to the keep turning it in the positive direction, but then it doubled back in the negative direction. So there's no contribution there. So it's a 0. And then you move it forward up to here, and now that was turning in the clockwise direction, but it's a half turn again, so I've got a minus a half, whereas the first time it went up to a half turn in the positive direction. So I'm counting half turns here is what I'm doing. All right, and then down here that's another half turn, and it's negative, because I'm still going clockwise. All right, and then there it's negative, another half turn negative, and I'm still going clockwise. And there is another half turn negative, I'm still going clockwise. And there it's another half turn up to here negative, I'm still going clockwise. Again, another half turn, I'm still going clockwise. Now this is a half turn counterclockwise, so that's a half turn in the positive direction. So that's a plus one half, and another half turn from here to here in the counterclockwise direction. So that's a plus half. Uh, and then I'm back to where I started. From here to here, I'm back to where I started. So you add up all the halves, positive and negative, and you get a -1.
Is this sometimes called a rotation number?
Uh, well, it's I think I've seen it. Well, if it was winding around just say a point, it'd be the winding number. All right, but I don't know. Maybe it's referred sometimes in the literature rotation, but I've always, from what I have seen, I've seen it as called the turning number. All right,
Okay.
all right. So AKA kind of a winding number of sorts. So yeah, I mean, if you stuck the if you took translated this tangent vector such that its tail was at the origin, and you just counted it going around, you'd get the winding number. All right, treat it as a unit vector. So it's -1. And the Euler characteristic is -1. So is this a coincidence? Well, it turns out that no, it's not. It's actually a result of an application of the classical Gauss-Bonnet result. And let me remind you what that is. This is from our students see this in a undergraduate differential geometry course on curves and surfaces. So you take a surface that's a Riemannian surface, so it's got a metric on it, and I want it compact and oriented, and with boundary. and you denote the Gaussian curvature of that surface by bold K, and the geodesic curvature uh, associated with the metric by little k sub g. And so you look at the boundary, and you orient this thing such that the orientation of the boundary and the orientation of the surface are consistent with each other. So kind of a right-hand rule type of thing, or Green's theorem type of thing. The standard way that we teach in third semester calculus. So you've got the boundary of your surface. You let it be piecewise smooth, so it's got so many vertices and then a smooth edges. And at the vertices, there's an ex there you there at each vertex there's an external angle associated with each vertex. All right. And then you get this relationship. Um, so this right here is the integral of the Gaussian curvature over the surface everywhere. So that's if we were to talk to our third semester calculus students, that would be a double integral or surface integral. With the area form right there. This is the distance form right here, and this is a line integral, and you're calculating that, and then you add up all those exterior vertices, and on the left you got all this geometry, on the right you got topology. All right, kind of the first theorem where you can say you're working in geometric topology. Geometry on the left, topology on the right. 2 pi times the Euler characteristic. In our presentation that we had of the surface, um, the Gaussian curvature is 0 because we've got the thing locally flat. There's the surface. You can put a chart, an atlas on this thing such that everywhere the Gaussian curvature is just 0. It's flat. Uh, uh, so based upon that presentation of the surface, uh, and the fact that the knot is smooth, there are no vertices. So this Gauss-Bonnet reduces to no vertices, and the Gaussian curvature is 0. So you just have this line integral here. All right. And you can see that with a little bit of effort, but you can see that what that is equal to is 2 pi times the turning number of the knot. The integral, the line integral over the geodesic curvature. All right. So this basic observation, and I will be honest with you, I didn't notice this until I started working in this problem, that this was one way to compute the Euler characteristic of a surface. Usually I did it the way uh, uh, our participant did it in terms of looking at uh, you know disk with handles on it and doing an alternating sum. Um, but we want to do this and exploit this way of thinking about Euler characteristic of surfaces for looking at closed surfaces in R3. But again, I want to give R3 some structure. And the structure I want to give it is this R2 cross R, because I want to have a natural direction on which we're going to project. All right. So onto the Euclidean plane. All right. So the setup is that you're given a surface of some genus. I want it again to be oriented, and and you can do this with, as we just saw, you can do this with surfaces with boundary, but for this thing, I'm going to do it with surfaces um, that are closed. So oriented surfaces that are closed and embedded in R3. And we're projecting them down onto R2 with this projection up here. And when you do that with a little fudge, with a little bit uh, of of um, and I'm gonna get rid of that. Where is it? Erase this. With a little bit of playing around, say with Sard's theorem, you can get uh, the um, um, th this G surface to be have a the set of critical points to be smooth possibly multi-component one manifold. The critical points are where the are not regular points. Regular point is where you look at the uh, this smooth surface over here with its smooth structure, and you look at the tangent plane into R2 cross R, and then you project it down onto R2, and the regular points are where the differential of this map is non-degenerate. It's non-degenerate, and the critical points is where it degenerates. All right. Those are so that set that is this uh, uh, multi-component one manifold is what we call the crease set. Um, and two embeddings are going to be in the same isotopy class if there exists an isotopy between them that keeps this crease set invariant. So here's the crease set. Here's an example, local picture. And as a matter of fact, uh, you can assume that this is the generic picture that you have. All right. Up here um, is where when you project down, say you pick a point right here and you project down, that's a regular point. Over here, when you project down, that is those are the critical values that you get up here because it's the tangent plane you actually see collapses to a line under the differential. So this crease set uh, is the curve back up here in the bedding that projects down by the our projection map onto R2 where it degenerates. You can have uh, a point that is kind of a corner where it's creasing one way over here and it's creasing the other way over here. And as you follow the one manifold, the crease set around, it comes to a point where it flips over. So right here, it actually degenerates down to the what is it? If you look at the differential, uh, it's 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 an its null set is zero. All right, from linear algebra. Um, the green arc in the left illustrates the crease set and it's smooth. The right indicates a corner or vertex adjoining two smooth arcs. All right. Uh, the easiest example that you can come up with, if you wanted to, is taking the standard two sphere in R3 and you project it onto R2 and the equator becomes the crease set. Uh, there is a sense if the surface is oriented, um, then there's a corresponding we can look at the orientation, and we kind of can get two flavors of what's going on with that crease set. Um, uh, since we're dealing with a closed compact surface in R3, then it bounds some three manifold, a handle body maybe, or if it was a copy of the two sphere, it bounds a three ball. If it's a copy of the of our S1 cross S1, the torus embedded, it bounds a solid torus, D2 cross S1. So there's an inside, there's a natural inside, and then there's the outside. And we want the orientation of the surface to be pointing away from the three manifold with boundary that it's the boundary of. So that's where we want the positive orientation to be for our setup. And so there's these two types of foldings that create that crease, local picture of the crease set. Um, a corner is going to be adjacent to both. So if you go back here and look at a corner, if over here is where the three manifold is, then over here is away from the three manifold that it is the boundary of. All right, and so it's where two of these are coming together at a corner. Give you an example. Um, you take, and we kind of called this the Cheshire Cat because if you go off and uh, um, uh, put eyes here and put so it kind of looks like a cat. So we were calling this the Cheshire Cat. But you take say a ball of clay, and you take a bar and you push it in to the ball of clay at a just parallel translated in. You're going to put in a dimple, and in fact you kind of want to take this bar and you want to tilt it a bit. So think of if you took a three ball that's made out of clay, and you were going to take uh, uh, something parallel to the x-axis, but you tilt it a little bit and you push in. Then when you project down onto R2 at the XY plane, you would get this crease set here where you got these two vertices here and here. So this is kind of one of the um, um, one of the first examples that we kind of found interesting. All right. So that's S2. There's we're going to want to get a handle on understanding the behavior around these corners. Because we're going to want to kind of apply Gauss-Bonnet to it. If you were to calculate at these corners the external angle of what's going on here, it you would just take um, there's two sheets coming into that corner. One sheet is like here it's you could take a piece of paper and put a flap and then another flap that goes underneath it. And then you could take a piece of paper that has just that sharp corner. And if you take this one on the left and insert it in between these two on the right, such that this green edge goes to this green edge here, and this green edge here goes to this vertical green edge there, then you'd be staring right down on top of a corner. All right, and there'd be that doubling back, or that corner there would be shown illustrating where two different types of folds coming together. Um, on this sheet right here, if we're interested in that angle of that external angle here, you just take a push off in this direction, and you calculate the partial turning between here and here. You can orient this in either direction, and you get that angle. You do kind of a similar thing here. You take a push off of a neighborhood of that corner here, and you get this loop that goes around. And so from here to here, you compute its external angle. All right. And uh, then suppose you looked at your surface and you looked at the complement of the surface with a crease set, you're going to get a surface, a connected component. And I actually want to take the closure of that to recapture the crease curve. So let gamma be a component that has corners. So there's so many corners here, and then there's so many smooth arcs. And the Gauss-Bonnet weight for k along this gamma, you'd go back to the way I just showed you to calculate those external angles. It's the uh, uh, that partial corner turning angle number over 2 pi. And then for each one of the smooth curves here, you calculate the partial angle of the turning number. All right. So on each component, K of the surface minus the crease set, we get this restricted Euler characteristic calculation just on that one on the close. So you take the surface, you embed it into R2 cross R, you project down, you get the crease set, then you go off and delete the crease set to get one of these to get a component. You take the closure of that component and you look at the boundary curves of it. All right, of the embedding of that closed component. And then you add up all the turning numbers for all those curves, and you'll get the Euler characteristic. So this right here is the Gauss-Bonnet applied to a surface uh, um, that is in the complement of the crease set. And the reason this works is because on that surface, we can essentially impose a Gaussian curvature that is flat everywhere. And so all you have to do is just compute the geodesic uh, uh, length along the boundary and add it up. So in general, you have this. If you take your surface and you cut it up into these components, and then on each component you compute its Euler characteristic, and then add it all up, because Euler character is additive along curves, then you'd be computing the Euler characteristic. If you don't have any corners, it's you can just add up all the turning number, all the curves in the crease set and multiply by 2. And the reason you multiply 2 is because each curve, each component in the crease set is on the boundary two of two Ks, two of these KIs. All right. So what I want to do is take this discussion and just restrict it now to S2 to see how this works in general. So the Euler characteristic uh, uh, weighting, the Gauss-Bonnet weighting of the collection of the simple closed curves with corners in S2 is uniquely determined. So once actually yeah, with oil is uniquely determined. Um, so here's the theorem that I want to show you. So um, so any collection of disjoint simple closed curves admitting a Gauss-Bonnet weighting, there exists a regular embedding of that surface into R2 cross R such that this system of curves realizes uh, an embedding that has this Gauss-Bonnet weighting. And by Gauss-Bonnet weighting, I mean the turning number with that's associated with that with a particular curve. So let me get to an example here. So here is a surface. I'll go back uh, and here's a surface. Um, and it's what is it? It's a pair of pants. And as I've drawn it here, I projected it flat onto the plane. And it doesn't really matter which way you orient it. But let's suppose for the moment that we're looking at the positive side of it. Then the orientation of the outside curve is going counterclockwise, and the orientation of the inside two curves are going clockwise. And with that orientation of the curve, boundary curves, it's consistent with the assignment of this being the positive side of that surface. Now you look at the turning number of these curves, and the outside curve is +1. It's going around counterclockwise one time. The inside two curves are -1. And so you if you add those turning numbers up, +1, -1, -1, you get -1, which is the Euler characteristic of a pair of pants. All right. By Gauss-Bonnet weighting, I mean you take your surface and you draw a bunch of curves on it, and you want your curve assignment to be such that on each component in the complement of your system of disjoint curves, that the weights add up to the Euler characteristic of the surface that subsurface that those curves bound. So here the weights would be -1, -1, +1, because that and if I add those up, I get -1. And there is an embedding of the pair of pants into R R3 such that when I look at it, those weights are actually realized as turning numbers. Uh, so um, so by Gauss-Bonnet weighting, I mean a weighting that corresponds to what conceivably could be turning numbers. And for S2, it'll turn out that uh, if you have a system of curves that work, then uh, then you will have um, an embedding. So let me just do this here. So so um, so here is a two sphere. All right, dot dot dot. And here is just one curve. I'm gonna put one curve on it. That one curve. Now that curve bounds a disk here and bounds a disk out here. And so it's Gauss-Bonnet, and the Euler characteristic of a disk is +1. So the Gauss-Bonnet weighting that would work would be +1. All right, but if I now do the same thing again with another sphere, uh, you'll see that that I'm in trouble. So here's another sphere. It's a closed surface that's oriented, and I can put in a what am I going to put in? Just two curves, one guy here and one guy here. All right. Now this curve bounds a disk right here. So I would try to put a weight on it of +1. And this curve right here bounds a disk here, and I put a weight on it of +1. But those two curves together out here bound an annulus whose Euler characteristic is 0. The reason I have to put a weight of +1 on this curve right here because it bounds a disk. Euler characteristic of disk is +1. Euler characteristic of disk is +1. Euler characteristic of this outside surface here is 0. So there is no Gauss-Bonnet weighting assignment to this configuration of curves on the sphere. Whereas this one over here, there is. If I had put in a third curve, I'd be all right because I could assign this curve a weight of -1, then this curve right here bounds a disk, so I've got a +1 weighting. That works. These two curves together bound an annulus. +1 -1 is 0. That's the Euler characteristic of an annulus. These two curves right here also bound an annulus. -1 +1 Euler characteristic of the surface that they co-bound is 0, so that works. And then finally, this inside guy is Euler characteristic +1, so that weight works. So that's a weighting assignment. And so if you have an embedding of a two sphere into R3 such that the crease set is smooth, then there always is a weighting assignment that is a Gauss-Bonnet weighting assignment that matches up with the Euler characteristic of the subsurfaces. The question is, if I give you an Euler a system of curves uh, with and you can put a weight assignment on it, can you build an embedding? All right. So that's the direction that we're going in. Let me get rid of all this. Okay. So the question is, does a collection of disjoint curves, when does it correspond to an embedding? And necessary condition is that the turning number of any component in the complement of the crease set, its turning numbers have to equal the Euler characteristic. So you need your turning assignments to be uh, making that correspondence, making that addition. So you have to have, so these would be your weights and they have to add up. All right. It turns out that if you give me a set of curves on the two sphere, there's a unique assignment, and it's sufficient for the curves. So going back to this idea of the pair of pants, here's one assignment, +1. I'm sorry, yeah, is that right? Uh, +1 on the outside curve, -1, -1. But that's not the only one because I could cut along here and cut along here and put a twist into it. And then I would end up getting something like this here and something like this here. And that again is flat. The um, Gaussian curvature you can put is 0 everywhere. And then if you check it out, you see that the turning number of this curve right here, it goes underneath. is plus 1, and the turning number of this curve now is plus 1, but the turning number of this curve right here, which used to be the outside curve over here, is minus 3. So you've got minus 3 plus 1 is minus 1. So I have it, so that works. The Euler characteristic of the pair of pants is minus 1. Over here you've got minus 1 plus 1 plus 1 minus 1, which adds up to minus 1. And here you've got now plus 1 minus 3. So by cutting along here and putting in these little twists, I can make this anything. So I can actually take any integers for a planar surface that has n boundary components, and if it sums up to n minus 1, then I'm good. All right, so here I've got 3, and it sums up to um, um, did I have that right? Any n integers, then we can always construct a planar surface with that turning number. Da-da-da-da. So here's an example. This is picture these curves on a two-sphere. All right. Picture these curves on a two-sphere. It's a how many I got here? 2, 4, 6, 8, 10, 12, 13. I got 13 curves. Right, 13 curves. I've labeled them gamma 1 through gamma 13. And so this is, picture this on a two-sphere. You're not seeing it wrap around infinity, but it's on a two-sphere. The assignment, and I've got weights associated with each curve. The assignment has to, you're totally forced into this assignment. And the reason is because the innermost guy, an innermost curve, always has to be a plus 1 because it bounds a disk. All right. And so you put a plus 1 on each curve that bounds a disk, and then you look at the next region, and the next region will have so many it will have so many innermost curves. All right. Here it has 2, or here it has 2. And so you're forced to make this curve right here weighted at minus 3, because this curve, and that curve bound a pair of pants. And the Euler characteristic is minus 1. So minus 3 plus 1 is minus 1. So every region here is basically a pair of pants, except for these innermost disks. Uh, and you see here, I'm forced to weight this minus 3 and minus 3. So I'm forced to weight this plus 5. All right. And in this case, I can consistently make all the weight assignments. As I showed you before, there are configurations on the two-sphere that have no weight assignment. You just can't do it. But here I can do it. So the question is, this is an, I'm working through a running example here. Can I find an embedding of the two-sphere in R2 cross R such that this is the crease set? All right, you have this configuration with a turning number minus plus 5, minus 3, plus 1, plus 1. And here's the construction. Da-da-da-da-da-da. Uh, Here's the construction. Um, Let me go back a page. Um, can I increase the size of this thing? I've got uh, I've uh, I've decorated these curves uh, on this pair of pants. I decorated them with either full dots or circles, and in between them, um, I've between each full circle and a dot, I put an arrow. All right. And it's that arrow where I cut and do this twist. All right. Now, the the solid dots I'm going to associate with what is this? A minus one with a plus one, plus two. And the empty dots I'm going to associate with a minus two. So you'll see that there's one solid dot on this curve right here. And right now the turning number is minus one. And so if you add that plus two to it, um, then plus two minus one gives you a plus one. Uh, but then I've got it adjoined by this green arrow to a minus two dot. And when I take this outside curve right here, which is which is turning around plus one, I've got two minus two dots on it. And so a minus two plus one, that's a minus three. And so there's kind of this weighting scheme where you draw a system of dots on the circles. They're either going to be solid or empty, and the solids correspond uh, uh, to plus two, and the empties correspond to minus two. And by running an arrow between a sol empty and a solid, that's giving you the balance such that you never change the Euler characteristic. So I'm adding a plus two and a minus two here, and adding a plus two and a minus two here to the turning numbers, to the sum of the turning numbers, and I always still get minus one. So it's kind of a bookkeeping scheme that we have. Um, so what I want to do with this is I want to put in those dots. And there's a methodology for doing this. And in fact, the methodology is kind of straightforward. Uh, you'll notice here that I've picked out, I've further decorated this configuration. And on some curves, I got a little black box. All right, and the way this is set up is there's a black box on this curve and a black box on this curve, and except for the disk regions, every region is adjacent to one black box. So this region right here is adjacent to that black box. This pair of pants here. This region right here is adjacent to this black box. And this region right here is adjacent to only one black box. And this region is adjacent to only one. And this is adjacent to only one. So you go off and make that initial assignment where you put a black box on so many curves, and with this feature that every region except for these disk regions, every region is adjacent to exactly one curve that has one black box. Then on those curves, you make your put in so many dots, all right, that you need. So I want a weighting of minus three here, all right. And so if it's the initial condition for a pair of pants is this outside curve is going to be minus one, and I want to make it uh, into a minus three. So I need two circles, and each open dot counts as a minus one. So initially this is a plus one, and I have to have two minus ones to add up to minus three. Minus two, minus two here, and the plus one gives me the minus three. And then everything else follows. So at the components where the black dots are, those if you make your assignments of how much more you have to add to it to get that turning number, then everything else is totally determined. And you're all and so you'll have a whole bunch of -2 open dots or empty dots on a curve, and then you'll have other curves inside your system that will be solid dots, and you draw your green arrows. And so this gives me a set of green arrows, and so this is a bookkeeping device that's going to show the embedding. All right, how to embed this thing. So here's the embedding, and you're just stacking it. All right. So this is actually an R3, R2 cross R. And what you're doing is you're stacking those regions that you had back here. This is like gamma 1, gamma 2, gamma 5. And this is gamma 1, gamma 2, gamma. So it's this pair of pants right here. And there's a systematic way of stacking these things up. But you'll notice I've stacked it up such that this edge path of arrows here, or this edge path of arrows here, or this edge path of arrows here, they all are above each other. All right. And this curve, this gamma 5 is going to be glued to this copy of gamma 5. So that's why I've got this identification here. And that point right there is the same as that point. Um, and you have stacking here, you have stacking here between here and here and here and here. So these vertical arrows that are have the double arrows at the end, that's telling you that this curve right here is glued to that curve, or this curve right here is glued to that curve, or this curve right here is glued to that curve. All right, so you do that gluing, and you end up just a local picture. You create that crease curve. So when I glue this guy to that guy, that's going to be my crease curve. And I've got these arrows stacked up here, and they project down to a set of crease curves. This crease curve here, this crease curve here, this crease curve here, here, and here, and here. And then the arrows all project down to a single arrow. All right. And so right now in this embedding, the boundary of these curves, uh, if you calculated the turning number, this is going -1 around, and this is going +1 around, +1. I'm sorry, this is going +1 around. I got it wrong. And this is going -1, -1. All right. And how to and going back to my original example of just where I took a pair of pants and I added a twist here and a twist here to get to change the turning number. Um, you're now gonna do that along this entire stack. So you've got this stack. It's an accordion type thing. You cut it along here and you twist the entire thing. And over each arrow. And so for each set of arrows here, there's a stack of arrows here, there's a stack of arrows here, there's a stack of arrows here. Is that 3 stacks? 1, 2, 3. There's 3 stacks of arrows. And for each stack of arrow, you're going to just give it one twist. And when you do that, you will realize the crease curves as having the associated Gauss weighting that you need. And at that point, the only thing to do is at the very, so you'll see that these arrows go from a +1 to a +1. And when you do that one twist there, this +1 curve becomes a -1. And that means it bounds a disk. And then you cap it off. This +1, when I take that accordion stack of arrows and do that one twist, this this end +1 curve right here, that means in three space it has turning number -1 and it bounds a disk. In three space, this will have a turning number -1 and bounds a disk when you finally do the twist. And the same thing here and the same thing here. You'll notice all these stacks of arrows start at a +1 disk and end up at a +1 disk. Same thing here. And when you finally do that twist along that stack of air, that stack, the last crease curve becomes a -1, which means it bounds a disk and you can cap it off, and that gets you your two sphere. And so you end up getting the embedding of a two sphere that whose has a crease set that corresponds to this. So for S2s, I can always build it. If I've got a configuration of curves that I can make a weight assignment to, a Gauss-Bonnet weight assignment to that is consistent with the Euler characteristic of the subsurfaces, then I can actually put it in three space as such that the turning numbers of the crease set realizes that turning assignment. Uh, Simplest examples of these guys is when you have your crease set, there's only three curves. And you ask yourself, how many different ways can I do this? All right. So there's a little bit of choice. Uh, I didn't talk too much about this. There's a little bit of choice in how you stack. Uh, but um, but in general, it's pretty rigid. So you'll notice I've got three crease curves, and as I showed you before, um, here's a two sphere, just a generic two sphere, and if I put three and if I have three curves on it, um, they kind of have to be concentric curves. So that this out here bounces this disk out here, so it's a +1. All right. This guy bounds this guy also bounds a disk here, so that's a +1. Then the third one, it co-bounds an annulus here and co-bounds an annulus here, so it has to be a -1 because the +1 and the -1 had to add up to 0, the Euler characteristic of the annulus. So how many different ways can you take this configuration and put it in three space? Well, it takes a little bit of argument, but there's exactly three. And we gave names to them. This one was called a saucer. There's this curve right here that is one of the +1s, and then there's another curve right here, the +1, and there's a crease curve right up here. So it looks like a saucer or bowl where there's kind of an outside and an inside. Whereas this is a mushroom, it's almost like an hourglass, where there's a crease curve here and a crease curve here. And so the direction you're projecting is down, obviously, for that crease curve here. And so this is a +1, and this is a -1, and then this is a +1. Then there's a thing that we discovered, and it kind of blew us away when we first found it, and we're calling it toric. It's hard to see, but what it is you take a saucer down here, and you take another saucer and flip it around, and you almost plumb them together, and you will get this thing. Another way of seeing it, let me get rid of all this. This toric one. Um, is you look at um, the reason and this is the reason we're calling it toric. You look at a that torus, that torus minus a disk. So here it is, and this is where we started off the talk. It deformation retracts onto two curves that are have the same zero cell. So an edge here and an edge here. So it's a wedge of two circles. All right. So now I've got this surface, which is a torus. All right. And so minus a disk. Now there are, as it is positioned in space, there are two compressing disks to it. There's one here that is above. Here's this compressing disk, and then there's one underneath. Let me pick another, maybe magenta. There's not one underneath here. That isn't right. Dot, dot. It's underneath. You can slap on a disk underneath here, underneath the surface, and there's one above. You take a regular neighborhood of this, thicken it up, take this torus minus a disk, take this compressing and attach these two compressing disks, and then take a regular neighborhood of that, and then the boundary of that, it will have three crease curves. This outside curve, the blue curve, and then there will be an inside curve here and an inside curve here. And if you check, well, we already know from the very beginning of the talk that the turning number of this outside blue curve is -1 because it bounds a torus minus a disk. But there will be a crease curve that is kind of parallel to this green curve here, and another crease curve that's parallel to this other green curve. So I think I'm going to stop there and ask if there's any questions. As a matter of fact, I probably should check the chat. Where's the chat? There's a number of comments in the chat. How do I get to the chat? Show the chat.
So Professor Rong asked, maybe it is the legendary node community
It's
that
not
uses
important.
it.
My comment is not important.
What's your comment?
Now, I was just saying, I think I heard the name rotation number from the legendary knot theory people, because they're
Oh,
interested in
oh,
classification of a
rotation. Yeah,
legendary
rotate. Yeah,
knot.
there's a
Yeah, there's like a certain
Yeah,
Bennigan number and
and then the
rotation number.
rotation number. Yeah,
Yes.
and that's something totally different. The
Oh,
rotation
that's
number,
different.
the rotation number there is comparing two different rotation with respect to a plane field. Yeah.
Okay, I try to
Okay.
understand.
All
Yeah.
right.
All right. Thanks.
Okay.
Any other questions? All right. Let's thanks Professor Menasco for the great talk again.
Well, thank you.
Thank you.
Thank you.
Thank
Thank
Thank you so much for coming.
Thank you for organizing.
Yeah, thank you very much for the invitation.
I'll see you in the future conference, Professor.
Okay. All right. Take care.
Goodbye.
Bye-bye.
Have a
Bye.
nice day.